Já tive, eu estou a falar para alunos de mestrado, é isso? Grande parte deles, não é?
Tem alunos do doutorado, da física, mas tem de outras áreas também.
Tem, tudo bem.
Então, e também tem alunos da graduação, também eu acho que tem alunos participando.
Ok, ok. Achas que já pode?
Isso. Peraí. Bom, isso aí, Fernando. Então, bom dia a todos que estão aqui participando da sala da pós-graduação, também quem está assistindo pelo YouTube. Para mim é um prazer apresentar aqui o professor Fernando Dias, de Portugal, é português, fez sua graduação, mestrado, doutorado, e a partir de 2003 assumiu uma posição na Inglaterra. E, bom, nós nos conhecemos de participar de eventos científicos, né, Fernando, também um projeto temos com o Andy, com o professor Andy ali de Durham. Mas o Fernando, assim, falar um pouco do Fernando. O Fernando tem mais de 5.300 citações, tem vários trabalhos em revistas altamente conceituadas, como Advanced Materials, Nature Communications, um fator H de 40, e é especialista nesse tema de thermodelayed fluorescence, de TADF, né, fluorescência crasada. E ele vai falar um pouco para a gente sobre os seus trabalhos nessa área. E muito obrigado, Fernando, você ter aceito de ministrar esse seminário à distância. Espero em breve, pessoalmente, aqui em Florianópolis. Será um grande prazer receber você aqui. Fernando, te passo a palavra e eu vou fechar a minha câmera.
Muito obrigado. Bom dia. Eu penso que ainda é bom dia. Como isto está a ser gravado para o YouTube, eu vou falar em inglês a partir de agora. Espero que compreendam. Se houver alguma coisa que ou o som não esteja a passar bem ou que não estejam a compreender porque eu esteja a falar muito rápido, digam e eu tentarei falar mais devagar ou tentar explicar as coisas de outro modo. Okay? So let's then start. So I was asked to give this talk and by Ivan, and to specifically to address the triplet harvesting mechanisms, and in particular directed to organic light emitting diodes. So these OLEDs that we have here. So before we start to the talking about the topic, let me just show you. Oh, okay, it seems that it has to be this way. So let me show you what Durham is. So Durham is a small and historical city in the northeast of England. So in this part here, so you have the Atlantic Ocean here, and in this part here is Holland. So London is here, of course, and we are like at 5 hours by train between Durham and London. Okay. So it's an historical city, as I already said. You have here the cathedral, is the most important monument in Durham. Is a quite impressive one. So if you have the opportunity to visit the city, I think that, well, you cannot miss it, let's say. So there are also, you know, there are several colleges that belong to the university. So the university is an important employer, let's say, in the old city and in the economy of the region. Let me just show you a better image of the city. So you see here, that is the river. This is like a peninsula. So you have here the cathedral. And so the university will be in this part here. So it's a very small city, and in particular for the Brazilian standards, is really, really tiny. You can walk around and see pretty much the whole city in one afternoon quite easily. Okay. So, but the advantage, because it's so small, we can very quickly go to, between different places and meet people and have a close contact with between physics and chemistry, for example, even biophysics or biology if we want. So it creates a really nice environment to do science, okay, and to live. So it's very safe city also. All right, so let's now start with the topic. So triplet harvesting is it means basically a process or mechanisms that we use to convert triplet states in an organic light emitting diode to make these triplets to contribute to light, to the light emission process. And you have here a slide, you see this EQE here, right? So this EQE, it means external quantum efficiency. And what I did is to write this efficiency separated in 4 terms, let's say. So the first one, you have the number of charge carriers that you inject in the device per second. That's what the current, this is the electrical current divided by the electron charge. So that gives the rate of electrons that are injected in the device. And if you go here in the top, what you see is that we have a glass substrate with a transparent electrode, more or less in this region. And then you have 2 layers. So this yellow one is to basically facilitate the injection of holes. The green one is to facilitate the injection of electrons from this other electrode here. It can be aluminum, calcium, something like that. And so part of this term here in the efficiency is basically the rate that these carriers electrons are flowing and are being injected on the device. And so once they are injected, they are transported through these layers, the yellow one and the green one, to this emitting layer in the middle. And so this emitting layer is where these electrons and holes, they recombine with each other and form excitons. And so that's the term here, is the number of excitons that are formed per second. That's the first term that controls the efficiency of these devices. Okay. Then a second term is that not all the excitons that we form are able to contribute to the light emission. So part of them, unfortunately, they are dark species, so they don't give origin to light in normal molecules. And the main reason for that is because we have the charges, electrons and holes, they have spins, and when they recombine, the spins can recombine in a way that they form a singlet state, like here, with the 2 spins paired, but they can also form in a way that they give origin to triplets. Spins are aligned in this type of configuration. And because there are 3 times more triplets than singlets, the end result is that we have just 25% of the recombination events origin to light in normal molecules. Yeah, these are the ones that can give origin to fluorescence. All the other 75% will be lost. Okay, so that means that this term here in the efficiency, if we use a normal molecule, will give origin it will be just 25%. Okay. So then the second term is from the excitons that are from the emissive excitons that we create per second. We need also to get those ones that emit with stronger emission. So basically, we need to get as much light as possible. All right. And so that is basically what we call the fluorescence quantum yield of our molecule. So it measures how efficient the light emission process is. And so it's a parameter that can also vary between 0 and 1. But while this one here is for a normal molecule, if we don't do anything else, is fixed at 25%, this one can be up to 100% if we use a good emitter, a good molecule. In most cases, it's much less than that, all right? Then the other part that we have of this efficiency is that from the light that is emitted, so from the photons that are emitted per second, not all of them are able to escape the device. Yeah, so you see the refraction index of these materials is much, and of glass is much larger than the refraction index of air. And so we have origin to total internal reflection, waveguiding. All this type of process will make the amount it escapes the device to be much less than 1. So this term is typically around 20 or 30%. Okay? So that means that the efficiency of most OLEDs is at most like 5%, if nothing else is done. All right? And so there are areas where we can do things to improve. And these are the two typical parameters that we can optimize. One is to maximize this ratio here. So getting some of these triplets to go back to be able to contribute to the light emission. So that means the converting triplet states into singlet states in some way, or allow these phosphorescence to be able to contribute. Okay, that is one of the parameters that we can optimize. And the other one is to maximize the amount of light that can escape the device. So some groups work, for example, trying to align molecules with the transition dipole moment aligned parallel to the substrate, because that will maximize the light that can escape. Okay, so there is a lot of work that can be done in this area, right? And so yeah, that's so getting molecules right. So for example, learning something from the liquid crystals that I know that you work with in that area. It might be interesting in the future to maximize this parameter here. But in this talk, what we are going to address is this other one. Yeah, so it's the triplet harvesting mechanism. So we are going to discuss two mechanisms in particular that can be used to maximize this conversion of these triplet states to singlet ones that can contribute to the light emission. So the most common way to do that, and the one that is known for a longer time, is using heavy metals. So basically designing molecules that contain metal atoms like platinum in this case, or iridium, which can then be used to convert these triplet states into, well, to make them able to emit light. Okay, and the reason why that happens is because the intersystem crossing, so the process that converts singlets into triplets, or vice versa, is enhanced in presence of an heavy metal. Okay, and so typically molecules that contain heavy metals like platinum or iridium, or atoms like that, will be able to emit from the triplet state directly. Okay, and that's why we call it organic phosphors, or organic metal complexes that emit phosphorescence. So they have typically triplet formation yields that are very high, close to 100, but they are also able to emit light. So we have been doing some work in this area, and specifically trying to address the emission in the near infrared region. And that's the reason why this example is here. As you probably know, when we try to get emission at long wavelength region, especially in the near infrared, is quite difficult, because the energy of the excited state tends to be dissipated through internal conversion, so basically vibrations, and which are a non-radiative process. And then in the near infrared, that effect is particularly enhanced, because the gap, the band gap, or the energy gap between the singlet excited state and the ground state is smaller, and so that makes this dissipation process more efficient. So this is known as the energy gap law. So one way to do that is trying to make the radiative rate faster, so it can compete better with the dissipation of energy through non-radiative processes. And that's the reason why in this molecule here we are using two metals. Okay, so we are aiming to do two things here. One is to achieve phosphorescence triplet state, and the other one is to maximize the luminescence efficiency at long wavelengths. All right. So it's a quite complicated or difficult process to achieve. So this is a good example. So you see here that we have these molecules. This is a paper that has just been accepted. So we have a quite well resolved absorption, but you see the emission here is already in the near infrared with very small component of the visible light. The emission, of course, at 77 Kelvin is more well resolved. This is artificial shifted down, so the emission increases at low temperature, of course. Yeah. So these complexes, metal complexes work, and in this case, so just to let you know, this is a good area an active area to work, where things are still not very well resolved, let's say, is to try to get OLEDs that emit in the near infrared. And the industry is quite strongly, they have strong interest in this area. So with this complex, we managed to do some devices. You see here, so these are devices made by evaporation. So we have quite part solution process. So this is a PVK, is a polymer, so it's not evaporated, but there are some layers that are made by evaporation. But we could achieve a quite nice, you see the electroluminescence is also in the near infrared with an efficiency of a couple of like 3 or 4%, okay, which it seems low, but in the near infrared region is quite good, okay. So going now to the other mechanism that we have as a way to harvest triplet states, which is going to be the main topic in this talk. So we will be addressing and describing this TADF mechanism. So as Eva already said, TADF means thermally activated delayed fluorescence, right? And so this is a mechanism that is known since the 1960s. And it was like, at the time, viewed as a bit of an academic curiosity, because the emission that we could get was very weak. But then since 2011, 2010, probably, people start to work in this area, and in particular the group in Japan of Professor Adachi, and he start designing molecules in a way that we could maximize this delayed fluorescence. So the mechanism is quite complicated, but of course we are going to start to describe it in a very simple way. And so in the first approximation, what you can think is that we have a singlet state and we have a triplet state, as any molecule will have. And so if we use light, we excite, we create 100% singlets if the excitation is made by is optical excitation, and then a part of these singlets promptly, in a way that we call it prompt fluorescence, occurs immediately after the excitation. But part of them will suffer inter-system crossing with this rate here, and will populate the triplet state. And because the triplet state, the transition between the triplet and the ground state, which is a singlet, is forbidden by spin, these triplet states will live quite a long time in normal molecules. So you have the singlets will live typically nanoseconds, but the triplets will tend to live like microseconds or even milliseconds. Okay? So there is a good chance, if we design the molecule in a way that the energy gap between singlet and triplet is small, that at least there is a Boltzmann distribution on the population here on the triplet states. So if there is a good chance that part of this population will be able to cross back to the singlet state in a process that we call it reverse inter-system crossing. So the rate for the reverse inter-system crossing, it depends on the energy gap between the singlet and the triplet, of course, and depends on temperature. Okay, that's why we call it thermally activated delayed fluorescence. So what happens is that once these triplets are able to go back to the singlet state, after they are here, they can then emit in a process that we call it delayed fluorescence, okay, because it occurs with some delay after the excitation has happened. A part of them will go back to the triplet state, and then the process repeats itself with the number of cycles, okay? And so you, at the end, in average, you get two components, one that is prompt fluorescence and the other one that is delayed fluorescence. Okay, that's the way this thing works. So if we go a bit more in detail to the mechanism, so what I did here is, this is for optical excitation. So I'm just saying here that we have the total fluorescence yield, so the total luminescence yield that we have from one of these molecules, as a component that is the prompt fluorescence. So once the singlets are formed, they will emit with this yield here, but they can also emit with the delayed fluorescence yield, going to the triplet state, coming back, emit, part of them emit, other part goes back and emits again, other part goes back, comes back and emits again. So that's what you have here. So you have the first process, okay, the prompt fluorescence yield, which is the fluorescence yield of our molecule. Then part of Pht is this part is converted in triplets, so this is the triplet yield. From these ones, this fraction of singlets that are converted into triplets, part of them will come back. So this is Ph, is the yield of triplets that are converted to singlets, and then they emit. And from those that have been created, you can have another cycle. So they go back again to the triplet state with Pht, they come back, and then they emit, and so on and so on. All right? So if you assume this process can carry on for an infinite number of steps, you end up with a series that is given by these expressions. So the total emission is basically the fluorescence yield divided by 1 minus the amount of triplets that are formed, the triplet yield, and the risk yield, so the yield of triplets that are converted to singlets. Okay, so that's what we have here. So one aspect that is quite interesting here is that if you have a molecule where the triplet yield is 0, so the fluorescence yield is potentially 1, which is the better emitter that you can have. But if the triplet yield is 0, using optical excitation, you are not going to see any delayed fluorescence at all. Yeah, because there are no triplets, so there is no delayed fluorescence. So you need to have some triplet yield in order to see delayed fluorescence if you use optical excitation. Even if you could have a risk yield, that would be 1, right? You always need to have some triplets if you are using optical excitation. But if you use electrical excitation, things change quite significantly. So under electrical excitation, remember, we form 25% singlets, and those 25 will behave in the same way as the optical excitation. So they will give this term here. But the other percent, they will come to the singlet state through this Phi-S, emit, and then they might go back with Phi-T, and then come back with Phi-S, and emit again, and so on. And so if you add the two components, you obtain this expression here. This is the total expression for the emission under electrical excitation. And so what you see here is that in the electrical excitation, even if you make the triplet yield equal to 0, you still can have quite high fluorescence if your singlet yield, if your risk yield is 1. All right. So you see, if we have both 0, let's say if a molecule has no triplet yield or has a triplet yield of 0 and the risk yield of 0, then the maximum emission that you can get is the fluorescence yield divided by 4, which is the typical fluorescence molecule that we have, right? But if we could design a molecule where the triplet yield is 0, so potential the fluorescence yield will be 1. If we can separate the triplet yield from the risk yield, then there is a good chance that we could 100% yield in electroluminescence, right? Which is quite, so this is maybe the $1 million question at the moment in devices is, can we get a way of achieving or designing a molecule with triplet yield equals 0, but a risk yield equal 1, right? Because that will be the ideal emitter, ideal TADF emitter, right? And that molecules could only be studied using electrical excitation if we want to see the contribution from TADF, all right? So that's where there are other aspects. For example, it's very easy to design TADF molecules that emit in the green. Very difficult to get them to emit in the blue region still, right? And it's the same with the metal complexes. So working in the two extremes of the visible spectrum is difficult. Getting molecules to give efficient TADF in the blue is difficult. Getting molecules to give efficient electroluminescence in the near infrared is also difficult. In between, in the green, everything is more or less okay. So we have a lot of emitters in the green region and very few in the blue and near infrared regions. Okay? So let's now try to discuss how can we design molecules in a way that the single triplet gap is very small, because if we want to achieve a strong TADF, we need to have a very small energy gap between singlet and triplet states. And that's what this diagram tries to show. So remember that once you excite a molecule, you promote an electron from the HOMO, so the highest occupied molecular orbital, to the LUMO, to the lowest unoccupied molecular orbital. So if you think about the Pauli principle, the Pauli exclusion principle, if these two orbitals overlap with each other, then the energy gap is going to be quite large. Yeah, because there is this exchange interaction that will appear, and the repulsion term also is, of course, higher in the singlet state than in the triplet, so that will split the two states significantly. So the basic idea is that if the HOMO and LUMO orbitals overlap with each other, the energy gap between singlet and triplet is going to be very large. If they don't overlap with each other, there is potential for the gap to be very small. And that's what we do. So we try to create molecules that have charge transfer states. So that means that the electronic density in the ground state exists in a different part of the molecule when the molecule is made. So there is a transfer of charge when you excite the molecule. And we also try to design the molecule in a way that these different parts, the HOMO and the LUMO, are aligned perpendicular to each other. Okay? So when we do that, the things seem to work, right? That's what we have here. So in this particular molecule, we have two what we call electron donors. So that's what we call, because there is this transfer of charge between the ground state and the excited state. You see in this particular molecule that we have the HOMO, so the highest occupied molecular orbital, which represents the ground state, let's call it like that. The electron density is localized in these two donor units, in these phenotizings here. Okay? But once it is excited, there is a transfer of charge to the middle unit, this dibenzo dioxide unit here. Okay? And so that's why we call this donor unit and this the acceptor unit. So what you see is that if we can align these donors and the acceptors perpendicular to each other, and the molecule will do that for us, you see when the dihedral angle goes from 0, so the molecule will be fully planar. You see this massive gap between the singlet and the triplet, but if the molecule twists these units approaching 90 degrees, the gap becomes very small. Okay, that's what we have here. And so basically that's the rule, that what we need to achieve is design molecules that have charge transfer states and align perpendicular to each other, the donor and the acceptor units, so they can have very small gaps between the singlet and the triplet states. And when that is achieved, then we have all the conditions to have good TADF. All right? So here, that's what we have. So this is now getting into the typical stuff that we do to characterize these molecules. So you can see here that we have, this is in black here, is the absorption spectrum of that molecule that I just showed you. And you have underneath, you have the absorption spectra of the single units that we just, we record the absorption spectrum of the two isolated units. And you see that the total absorption spectrum is basically almost a simple sum of the absorption spectra of the two units. Okay? We also have the emission of both acceptor and donor units when they are alone by each other. And here in black and in this orange, you have the emission of the total of the full molecule in two different environments. So MCH is the liquid solvent. It's a non-polar solvent, so the emission appears quite good shifted. Xionex is also quite non-polar, but is a rigid polymer, right? So it creates a rigid environment for this molecule. And so what from that, you see that the emission appears quite red-shifted when compared with the emission of the two units. This is typical of a charge transfer state. And also, you see that the energy of this state, we can measure it. So we know where the singlet state is. And we can also measure the phosphorescence. That's what is here on the right. You have the phosphorescence of the full molecule and the phosphorescence of the two isolated units. And you see again, we can measure the triplet energy from the phosphorescence, and you see that is really very similar. Okay, so we have an energy gap between singlet and triplet of just 20 milli-electron volt, so which is comparable to the KT value at room temperature. And so we have created the conditions to achieve strong TADF, and that's exactly what happens. So if you look at the decay of the emission of this molecule, you see that we have a component of prompt fluorescence. That's the decay that you see here. So this is emission counts per second, or count, sorry, and here time. So we go from nanoseconds or to milliseconds, right? So you see a first component that is just the prompt fluorescence decay, and it decays with like 15 nanoseconds. And after that, you see another component which decays with a lifetime of 5 microseconds. You can look at the spectra on these two regions, and that's what we did here. So you have, this is time resolved spectra obtained at different delay times. So there is a spectra at 2 nanoseconds, which is pretty much here. Another one at 50 nanoseconds, probably there, right, more or less. Another one at 1 microsecond, so something like here, and so on, 40 microseconds, like that. And you see that the spectra overlaps completely, which is a signature that the emission is, all the emission is coming from the same state, which is the singlet state, right? However, when you cool down, right, so you go to low temperature, you see that another emission appears, and you see that this emission here, 258 EV, is exactly the emission that we have the onset of the phosphorescence. Okay, yeah, so this is the same spectrum, basically. So this is the phosphorescence that you have at low temperature. We can see also phosphorescence, and we can see the delayed fluorescence. So over time, at low temperature, we have two emissions from the triplet state, as which is still able to occur, surprisingly, but also some phosphorescence. Okay, that we are really looking at delayed fluorescence, and we are looking at a thermal activated delayed fluorescence. We need, of course, to have a look and to check how this emission changes with temperature, and that's what we did here. So this is the spectra of the delayed emission recorded as a function of temperature. And what you see is that, so the 20 Kelvin is somewhere here, very weak emission, but as we go and we increase the temperature, the emission gets stronger and stronger and stronger. So this is the typical signature of a thermal activated process, okay? And by looking at this represented integral of this emission as a function of 1 over temperature, we can get the energy barrier for this process in a typical Arrhenius type plot. And again, we managed to determine something around the 20 milli-electron volts, which agrees completely with the singlet triplet gap. So this is clearly TADF. And even to be even more sure about that, we also check the power dependence. So basically, as a TADF process occurs in a single molecule, so if we create more and more excited molecules, doesn't matter, because if the process should be linearly, should be directly proportional, and so the emission should increase with gradient 1 in a log plot, and that's what we have here. So this basically represents all the tests that are needed to confirm that the molecule emits TADF, and that's what we did here with quite good success. So the next step, of course, is to apply this molecule in devices, and we did that as well. So you see a typical, very simple device here. Remember what I told you, in a normal device, using a normal fluorescence emitter, even if the fluorescence yield is 100%, you should get no more than 5% efficiency. In our case here, with the TADF, we got like maybe around 14%. Okay, that's what we got with this molecule. But our now devices are now better emitters, and maybe also better devices, so optimized already, where efficiencies can go up to 25% or even a bit more than that. Okay, so TADF works and has been a quite huge. There are still problems, as I told you, so we can still work in and trying to optimize the molecules better, as I described in this $1 million question, but also working in terms of stability of the molecule. And the effects of stability, that's what you see here. As we increase luminance, so we increase current in our device, you see that the efficiency drops significantly. That's what people call the roll-off. Yeah. So is a very complex issue on devices at the moment. Pretty much all of them are affected by this effect. Okay, and there are many reasons for that. It can be caused by the interaction of triplet excitons with other triplet excitons. Most probably will be due to interaction of these triplet excitons with charges, and so that's a major issue. All right, so the charges tend to quench the triplet population, and so the emission will drop. It can also be, and most probably is, caused by the degradation of the molecule. So we need better molecules. We need molecules that are more stable and not so prone to suffer from degradation. And that's the two main, let's say, or three main questions in terms of OLEDs at the moment. So achieving blue emission and near infrared emission, that's one of them. Efficient triplet harvesting in these two regions, and also in the green, and improve stability. All right, so trying to solving these questions is also interlinked, right? Because if to minimize this interaction with between excitons and charge carriers, what we need is to design molecules that emit with a shorter lifetime, so they decay, they release the energy in a faster way. And so that is related with the mechanism that we use. So can we come up with some new mechanism that give us a better or a faster decay time? That's a good question to try to answer. All right, or can we shield our emitting state from the interaction with charges? That's also important. Okay, so I'm just going to show you another work that we did recently, or more recently than this one, just to show you what people are also trying to do around the mechanism. So these are an example of a collaboration that we have with a group in China, in the University of Wuhan. And so they are working with molecules that have, instead of having just one donor, one acceptor, what they did is that to have the donor, so this is a carbazole and an acceptor here, both linked to this bridge, okay? And the bridge is important because then they can change the number of donors. So in this case, there are 2 donors and 1 acceptor. In this other case, there are 3 donors and 3 acceptors, all right? The reason why that is important is because by adding donors and acceptors, we are going to change the density of states where the risk, the interconversion can occur. And so if you remember the Fermi golden rule, so the rate of interconversion between states depends on the density of states, right? And so if we increase the density of states, we have a faster rate. And that's the purpose of this design. There is also another important thing here, is that there is the possibility, at least in this more crowded compound, that the charge transfer occurs through space and not through bounds, which is quite interesting. Okay, there are just very few reports of through space charge transfer in this topic in the TADF field. This is one of them. We think in this case that there is really through space charge transfer taking place. Anyway, so what we hear again, that the HOMO, so this is the HOMO and the LUMO, they are in different parts of the molecule. So in the particular one, you see the 3 donors with the HOMOs, and then just the LUMO on the 3 acceptors, or yeah, the other one is in some orientation. And also you can see the density of states that you have now. So when you increase, you see when you have just 1 donor, 1 acceptor, the density of states is much lower than when you go to the 3 donors, 3 acceptors. And that increases the rate quite significantly, or at least we expect that effect. So then we did the usual things. So basically what you see here is the absorption and emission and phosphorescence, so fluorescence and phosphorescence. Unfortunately, the gap is still a bit large, just a donor and acceptor. But when you have the 3 donors and 3 acceptors, the gap is pretty much none, or at least on the order of these 20 millielectron volts or so. And you see what happened here. So this is the emission, the decay of the emission when oxygen is present and when there is no oxygen. So this is important because oxygen quenches the triplet states. So one way, a quick way that we have to evaluate if there is a contribution from the late fluorescence is to remove oxygen. And so in the first, when there is only 1 donor and 1 acceptor, it doesn't make a huge difference. When we increase the number of donors and acceptors, the contribution of this delayed fluorescence increases, and here is quite significant. All right. So again, proves that the system, the strategy works. You can see it here also as a function of temperature. So you see that there are delayed fluorescence in all 3 compounds, but if you look at the ratio between this amplitude at time 0, you see that the ratio is much more favorable in this case where we have 3 donors and 3 acceptors. The power dependence is also 1, which again proves that we have the delayed fluorescence and is thermally activated. And the final issue, of course, is to look at just trying to look at some parameters here. This is quite small numbers. Let's see if I can increase this. So you see here that we achieve a quite strong yield, 76%. And you see the lifetimes, they are also quite fast. So just 1.6 microseconds with a very small gap between the singlet and the triplet state. So, well, now it works in a nice way, right? Okay, so then we did the devices, and we see that these devices work quite well. So again, we achieve efficiencies around 20% or so. With there is no much roll-off, but of course, if we increase the current density, if we go to higher current densities, probably we'll see the roll-off appear again. That's not been solved for sure. Yeah. So there are still a lot of work to do here. The good thing about this device, it might seem not very important, but it is. This is a device done entirely from solution. Okay, so it's not evaporated, and is a device that uses only a single layer. So there is no host working in this device. So which allows to facilitate more and potentially to move towards electronic inks. We will be able to produce devices from standard printing processes from solution, which was a long-standing aim in this area. Okay, so I think the time is already long for this seminar, so I'm just going to finish with some acknowledgements. Here is just a table with the efficiency. So yeah, I told you already that we had like here is 21%, just for you to see. Okay, and it's pretty much in the not the best blue, but is quite good. Okay, so let me just give my thanks to the people that have been involved in along the years in this type of works. So working with me in Durham, so I had Roberto. Roberto is now back into Brazil, so he's already a lecturer, a professor in one of the Brazilian universities. I don't remember now the name. It's close to Berlândia, and is starting his research there and trying to establish his own group, which is good to see. He was my first PhD student here at Durham. Rong Juan is also back to China, so she did the PhD with me as well, and is now back and starting to work in China. Piotr he did the PhD with me as well, but is now a postdoc in my group as well, so working in these near infrared emitters and devices. Shemek he was a visitor here, so he's a professor in Poland, and he has a very active group back in Poland, where he's doing a lot of photophysics and electrochemistry in this type of molecules. We have a good collaboration and very strong collaboration with the group of Professor Bryce, also in Durham, that does a lot of these materials for us. So Jonathan is now in Liverpool, but he did some of these molecules. Zhongji is back in China, is a professor in China, and also did some work for us in mainly in polymers. And Andre does a lot of this X-ray stuff that we use. For theoretical work, we have a nice Thomas from Newcastle, so he's a city near Durham. And James is one of his students, and he did part of the work in theory for us. And finally, on this work that I just introduced you, just present with the charge transfers through space, I have this nice collaboration with people in the University of Wuhan in China. So they did all these compounds and the devices. They also did the devices. So in this particular work, our contribution was just on we did some of the measurements on the photophysics and helped with the understanding of the mechanism. Okay, this is the end. So thank you and patience to come to this seminar and to try to listen to the presentation. And I hope I did it in a way that you could. Okay. Right. Yeah, back to you.
Hi. Wow. Yeah. Thank you very much, Fernando, for your wonderful presentation. it's interesting to see, as you said, yeah, you know, the application of TADF in OLEDs is something like 10 years old, yeah,
Yeah.
and in this time a lot of things were improved, and this is because the possibilities that were open. Yeah? But I'm curious, do you know if there are already TADF OLEDs on the market? Are the companies already producing OLEDs with TADF or not?
That I'm aware, no. I think they you know, industry is much slower to introduce new things. Okay, so once they have a process that works, I think they only change to something that is new, let's say, if there is a good reason for that. Okay, so I believe, I'm not completely sure, but I believe that most OLEDs that are in the market at the moment work with metal complexes because it's an older technology, let's say. So they use metal complexes for the red and for the green, and they use pure fluorescence emitters to the blue. And so they use these three. The group of Professor Adachi in Japan, they are trying to work, or they are already working actually, with the companies. I think even from a startup that they have created, where the idea is to use the TADF molecules and then link this TADF emitter through energy transfer with fluorescence emitters. Because that's also important. I didn't mention that, but it's also important, is that for displays, the TADF are not the best thing because they have this broad emission, right?
Yeah.
And so for displays, it's important to have some narrow emission that you can give a quite narrow and well-defined color. And so for that, TADF is not good. So what people do is to use energy transfer. So the TADF molecule works as a triplet harvesting unit, and then the energy is transferred to a fluorescence emitter with a very strong yield and narrow emission. And so they have created this mechanism which they call the hyperfluorescence, and they work with that. I think they are already introducing some of these inks, let's say, or these compounds for displays in I think it's like Kylux or yeah, sub company that they have created.
Yeah, there are also people working actually also in your group, I think, yeah, with this TADF Exiplex emitters, yeah.
Right. Yeah.
And what's actually the advantage of this system?
Sorry, can you repeat?
What is the advantage of this system?
Well, there are many. Let's say, in terms of TADF, I would say that there are not much advantage. Okay, because what we do with normal TADF molecules is that we have an Exiplex as well. All right. So the difference is that instead of using two separated molecules, we have one single molecule. So, but the Exiplex, the intermolecular ones, so the separated ones, they might present some advantage in the way of in simplicity. Okay, if you get them to work, it might be easier to synthesize and cheaper to synthesize these separated units and then just put them together.
Yeah, just mix, yeah.
Yeah, and that might bring some advantage. All right. These systems are really very interesting in terms of physics, and because they are quite similar to the situation that we are trying to do research in solar cells and photodetectors. All right, because organic solar cells also work with the blend of two molecules, and in that way there are quite similar thing between the two technologies. But they are less explored than normal TADFs, all right? And they also have the physics, the mechanism is still not very well understood, okay? So from the point of view of light emitting devices, I wouldn't say that there is a clear advantage, let's say. Apart of they are simpler, and you can use, for example, one single acceptor and then several different donors to create emission in different regions. Okay, yeah. So you can do things quite easily. While if you go to different molecules, it gives much more work because it depends on the way these two units are connected to each other. For example, if you go and change the position of one donor relative to the acceptor, the TADF photophysics changes completely, right? In most molecules, there are molecules where we can switch on and switch off the TADF by changing the position where the donor and the acceptor are attached in the molecule. And that's why TADFs are quite complicated. Okay?
Yeah, you're right. And about the blue TADF emitters, this is still a target, yeah. And what's the main difficulty on obtaining these materials? And do you know what are promising materials? For example, we are working with copper complexes, yeah, that are showing blue as blue emitters are. What's your opinion about this?
So copper complexes, you know, they appear in some years ago. People start even before the TADF. So the whole idea was to, you know, because iridium and platinum and all that stuff is quite expensive and creates problems in terms of, well, if we start using these molecules in a quite wide application, they will create problems in terms of environment and all that stuff, or may create problems. And so the copper appeared as a cheaper alternative to these heavy metal complexes. I did a few works on that, and what we had mainly, it was the efficiency was much lower. Okay. Yeah. And one of the reasons was that the internal conversion, so the dissipation of energy, is much more efficient when you have the copper. Also, probably because the intersystem crossing is slower, and so the overall performance was worse. All right. I don't know the situation at the moment. If there are some more efficient copper complexes now, and some of them showing TADF. So it's not an area where people are working and trying to come up with new and better materials, let's say. But there are still a lot of problems to solve on that area. So you can see all these kind of alternatives. You can see normal exciplexes, donor-acceptor exciplexes, like the ones I showed here. There are people now, for example, we have work to be submitted where we are exploring TADF also in platinum complexes, which is quite interesting. So there are many alternatives as usual, all right? But the main questions remain, the ones that I indicated in the presentation. The main questions remain and affect all these areas. Okay.
And the blue emitters, TADF emitters, there are very not so many examples about it. But what's the main difficulty in the blue?
Well, it's stability. And efficiency. The stability is a problem in all regions of the spectrum. Okay, but particularly in the blue region, because you have to work with a singlet level that is quite high energy, and you have to have TADF, you have to push the triplet state also quite high. Then in order to have a host, the host has to have a triplet state even higher, So all this stuff makes the things complicated, and together with that, the stability of the materials is weaker, of course. Yeah, that's why there are no metal complexes working in the blue. Yeah, no one managed to get a good metal complex with strong emission in the blue region. And with the TADFs seem to be a bit better, and there are a few examples of molecules that emit electroluminescence in the blue and potentially can be used, but still I think this, when you look at the overall device, the stability, so the roll-off on the efficiency is still poor. Okay, and so that needs to be solved, right? That's the main reason. Okay, actually I would say that more at the moment, more than improving the efficiency, maybe the most important thing is to improve the stability of the devices. Okay. So it's much better to have a device working at 8% or 10%, but with a strong stability, than having a device that works at 25%, but with low or poor stability.
Yeah.
So that's where I think is the main issue.
Yeah, you're right. And you also did a comment here about the solution processing device was also a target. Yeah, but is this still a hot topic? Are people looking to have solution processing devices?
Yeah, there are people working on that. For example, we are working on that. So most of these devices that we did with metal complexes are at least in part doing by solution. Again, it's the same thing. When what people start to note is that you can achieve much better efficiency in vacuum process devices. All right. And the reason is that you can fabricate devices with several layers. All right. Yeah. So you can put transport layers, you can put blocking layers to force recombination away from the electrodes. All that stuff contributes to a strong emission. When you get the solution process devices, it's more difficult. Yeah, because you can only add like 2 or 3 layers. And so the efficiency drops quite significantly. And so it makes these devices much less competitive. Yeah. However, they are also cheaper. And so if we manage to produce them in a way that again they are stable, even if they have less efficiency, they are a good alternative in some niche applications. Okay. So of course, for a very good display that industry can sell by £1,000 or something, or even more, you know, the deposition by fabrication by vacuum deposition is interesting. But you want to produce applications like very cheap labels or something like that to put on clothes or on, you know, on food targets or something.
For illumination.
Yeah. Then you want to have something that is very cheap. And even stability is not so important because you want to get something that works just for a few hours. All right. And in that type of application, solution process is good. All right. So everything depends on the application that you are targeting, and the market that is your target as well. All right.
Yeah. Right. And now, you know, finally, just to make a comment, in the beginning you said about this, the molecular orientation. Yeah, the interface is also an issue to get more light out of the OLED. Yeah, and you mentioned about the liquid crystal application. I know in the past people were talking about it, but do you think this is also is a hot topic because we are, we are working with these liquid crystalline materials that can be aligned, and if we can succeed to get alignment in the interface and to get also aligned the matrix or the emitting molecules,
Well, I never work with liquid crystals, to be honest. Yeah, so I cannot give you a detailed let's say answer about using them. Okay, but the idea here is that if you can get molecules that align with the transition dipole moment parallel to the substrate, and that in a way that they self-align, so they have some auto-organization, let's say, that is a hot topic. Because that, let's see, for example, let's forget about the TADF, okay, or about metals. And so the efficiency, you are working with two main parameters. One is the single triplet yield, the other one is the PLQI, and the other one is the alignment. So you have three parameters, all right? So if you work with typical fluorescence emitters, so one of the parameters is just 25%, okay? And then you can say, well, with the output coupling, because that drops significantly, like in a normal molecule to 20% or so, then yeah, we have just this 5%. But let's imagine that you can maximize that alignment process, because if the molecules can align, you can maximize this output coupling. So you get it like 0.4, 40% or something like that. So if you have a strong fluorescence yield, let's assume 1, just to facilitate our calculation, you are going to have 25% times 40%. Okay? And that is already interesting, all right? So if you have that, let me just do the calculation here. 0.25 times 0.4, and you have like, 10%. Okay? So you will achieve potential of 10% efficiency, or even a bit more, and potential with better stability, right? That will be already good. If now you can put also some triplet harvesting, right? If you can add some triplet harvesting, so instead of 25%, you can get like 50%, then it becomes really very interesting, all right? So I would say that getting molecules that will self-organize in a way that you want, right? So parallel to the substrate is a very important thing, right? The question is, how can we do that? And so I don't know if the liquid crystal will give you some idea or some direction for that, to design some strategy to achieve that alignment or not. Clear a way where you can try to do it.
No, there are some strategies to align these materials that are well known in the literature, but the main thing now, actually, we are working with Harold Bock. He is a chemist in Bordeaux in France, and he designed disc-like molecules that also present nematic phase that can be aligned, and the idea, we are selling the idea that they could be good matrices, to dope with like TADF emitters or something. But we are actually now working on it, and the main, as you said, the main target that we need is to achieve the alignment, and also to investigate if they are actually good, if they have good energy levels for acting as a matrix.
Yeah, that's true. That's true. That's a good area for work, of course. Yeah. But if you could put together strong emitters that align in some way, or that you can manipulate or trying to control the alignment, yeah, that would be very, very good to see.
Yeah. Okay, it's good to hear that. Yeah, when next year, if I'm in Durham, we can talk better about it, and probably I will have some materials of this kind of materials to work there.
Yeah, I hope so. So let's see if this virus stuff disappears quite quickly.
Yeah.
So we can meet and have some good wine around.
Very good. Okay, Fernando. So I would like to thank you very much. Yeah, it was really interesting and a pleasure for me. Yeah, to talk here and that you are presenting the seminar in our graduate program. And as I said in the beginning, I hope to see you here in Brazil soon. Yeah.
Yeah.
And,
okay. I'll, as soon as this thing goes away, I will try to correspond.
Yeah. You know, Andy, together with Andy, we were organizing this optical probes conference. Yeah, it will be next year in March, but then we postponed it for one more year. And
right, yeah, you did well. Yeah, that's important. Yeah, I think March was too soon. So yeah, so by then the things have cleared probably, and we can start traveling again and meet friends and co-workers, right?
Okay, so I would also like to thank people that are here participating, and thank you again. And abraço, Fernando. Tudo de bom.
Eu espero que os estudantes tenham. Eu tentei falar o mais devagar possível. Espero que eles tenham percebido o meu inglês, que não é 100% inglês aqui da rainha, mas
não, mas você sabe que assim é sempre mais fácil entender o inglês de um estrangeiro que não é nativo, né?
É verdade. Eu entendo melhor o inglês falado pelos americanos do que muitas vezes o inglês aqui de Inglaterra.
É verdade. Bom, tudo bom, Fernando. Obrigado novamente, um abraço, até breve.
Adeus. E um abraço para todos.
Tchau, tchau.
Como é que eu posso parar isto?